Every time you type a question into ChatGPT, something happens that you cannot see. In a data center somewhere, thousands of specialized chips fire up simultaneously. They consume electricity measured in kilowatts. They generate heat that must be dissipated by cooling systems that consume millions of gallons of water. That single query probably used enough energy to power a light bulb for an hour. It probably evaporated several milliliters of fresh water. It probably emitted a measurable amount of carbon dioxide, depending on whether the data center runs on renewable energy, natural gas, or coal. Now multiply that by the billions of queries that happen every single day across every AI chatbot, every image generator, every video creation tool, every code assistant, every enterprise AI deployment. The numbers are staggering, and the AI industry is not talking about it. The technology that promises to solve climate change, cure diseases, and advance human knowledge is itself becoming one of the largest and fastest-growing sources of energy consumption on the planet. And it is happening faster than anyone predicted. I have spent weeks researching the true environmental cost of artificial intelligence. What I found is alarming, fascinating, and far more complex than the simple narrative that AI is either good or bad for the environment. Let me break it all down for you. Let us start with the raw scale of AI energy consumption. In 2023, the International Energy Agency estimated that global data center electricity consumption would double by 2030, reaching over 1,000 terawatt-hours per year. To put 1,000 terawatt-hours in perspective, that is roughly the total annual electricity consumption of Japan. Every building, every factory, every home, every train, every streetlight, equivalent to what the AI and cloud computing industry alone could be consuming. And here is the critical detail that most coverage misses. That 2023 projection was made before the explosion of generative AI, before ChatGPT became a household name, before every company on Earth started building AI features into their products. Recent revised estimates paint a much more alarming picture. Researchers at the University of Massachusetts and the Allen Institute for AI project that AI workloads could consume over 500 terawatt-hours annually by 2028, just 4 years from that estimate being made. Goldman Sachs published a research note that crystallized the scale of the problem. They found that a single ChatGPT query consumes approximately 10 times the electricity of a standard Google search. 10 times! For one interaction. Think about the implications of that number. Every time someone chooses to use an AI chatbot instead of a traditional search engine, they multiply the energy cost of that interaction by a factor of 10. At current adoption rates, the cumulative impact is measured in the annual electricity consumption of medium-sized European countries. Training AI models is even more energy-intensive than serving them. Training OpenAI GPT-4 is estimated to have consumed over 50 gigawatt-hours of electricity. That is enough to power approximately 6,000 American homes for an entire year. For one training run of one model, and training is no longer a one-time event. Companies now continuously train, fine-tune, and retrain their models. Each generation requires more compute than the last. GPT-4 used more compute than GPT-3, which used more compute than GPT-2. The energy curve is not flattening. It is accelerating exponentially. Sam Altman, the CEO of OpenAI, acknowledged this reality at the World Economic Forum in Davos. He said, and I am quoting directly here, "We need an energy breakthrough." He was not talking about making AI smarter. He was talking about the physical impossibility of powering the next generation of AI without fundamentally new energy sources. Altman was not being alarmist. He was being realistic. At current efficiency rates, training a hypothetical GPT-5 or GPT-6 class model could require a dedicated power plant. Not a data center, a power plant. And that is just for training. Serving the model to hundreds of millions of users would require several more. But electricity consumption is only half the story. The other half is water. And this is where things get genuinely disturbing. AI data centers generate enormous amounts of heat. Every chip, every server, every rack is converting electricity into computation and waste heat. That heat must be removed, or the equipment fails. The most common cooling method is evaporative cooling, which consumes water, huge amounts of water. A study from the University of California, Riverside, led by researcher Xiaolei Ren, calculated that training GPT-3 in Microsoft data centers consumed approximately 700,000 liters of water. That is enough to fill a nuclear reactor cooling tower. For one training run, Microsoft's own environmental report revealed that its water consumption jumped 34% between 2021 and 2022, an increase of nearly 1.7 billion gallons. The primary driver? Expanded AI and cloud computing infrastructure. Google reported a 20% increase in water consumption over the same period. The company disclosed that its data center in the Dalles, Oregon, withdrew over a quarter of the town's total water supply in a single year, and they plan to expand that facility. In water-stressed regions, this consumption creates direct competition between AI infrastructure and human needs. Farmers are competing with data centers for water allocations. And AI is winning because data centers generate more economic value per gallon than agriculture. The town of Goodyear, Arizona approved a Microsoft data center campus that will consume 56 million gallons of water annually in the Sonoran Desert. During a multi-decade drought that has forced the Colorado River into crisis. The data center will use water from the same watershed that supplies Phoenix, Los Angeles, and millions of acres of farmland. Google is building a $600 million data center in Mesa, Arizona, that will consume up to 4 million gallons of water per day at peak operation, in a region where residents are being asked to limit shower times and let their lawns go brown. Meta is constructing a data center in Los Lunas, New Mexico, that drew community opposition specifically over water concerns. New Mexico is one of the driest states in America. The Rio Grande, which supplies the region water, is regularly reduced to a trickle in summer months. The global picture is even more concerning. In Ireland, data centers now consume more electricity than all rural homes combined, prompting the government to consider restricting new data center construction. In the Netherlands, data centers were briefly banned from new construction in parts of the country due to grid constraints. Chile is experiencing a data center boom driven by AI, with companies attracted by cheap renewable energy from the Atacama Desert solar farms. But local communities are protesting, arguing that the energy should go to Chilean homes and businesses, not to foreign technology companies. Which brings us to perhaps the most surreal development in this story. The AI industry is now turning to nuclear power, and I do not mean as a symbolic gesture. I mean as a core business strategy. In September 2024, Microsoft signed a deal with Constellation Energy to restart a reactor at 3 Mile Island in Pennsylvania. 3 Mile Island, the site of the most famous nuclear accident in American history. The reactor that was not damaged in the 1979 partial meltdown will be restarted specifically to power Microsoft AI data centers. The deal is a 20-year power purchase agreement. Microsoft will buy every megawatt the reactor produces, paying a premium above market rates for carbon-free 24/7 baseload power. The reactor, which was shut down in 2019 for economic reasons, will be renamed the Crane Clean Energy Center. Amazon is following the same playbook. The company purchased a nuclear-powered data center campus in Pennsylvania from Tallinn Energy for $650 million. The campus includes direct access to the Susquehanna's nuclear power plant, giving Amazon control over the entire energy infrastructure. Google is taking a different approach to nuclear. Rather than buying existing reactors, Google is investing in next-generation small modular reactors, or SMRs. These are smaller, cheaper, theoretically safer nuclear reactors that can be manufactured in factories and deployed incrementally. Google signed a deal with Kairos Power to purchase power from a fleet of SMRs that are expected to come online in the early 2030s. The first reactor is projected to deliver 500 megawatts by 2030, with additional reactors following. And Sam Altman himself is deeply invested in nuclear. He personally invested $375 million in Helion Energy, a nuclear fusion startup that aims to commercialize fusion power. He is the chairman of Oklo, a company developing micronuclear reactors. His bet is that AI cannot scale without nuclear. There is something deeply, darkly ironic about all of this. The technology companies that sell AI as a solution to climate change are now the primary driving force behind restarting decommissioned nuclear plants, building new ones, and investing in fusion. AI was supposed to solve the energy crisis, not exacerbate it. But I do not want to be unfair. The story is genuinely complex, and the net environmental impact of AI is not purely negative. AI is being used to fight climate change in important ways. DeepMind famously reduced the energy used for cooling Google data centers by 40% by deploying AI to optimize cooling systems in real time, responding to weather conditions, server loads, and thermal dynamics. The same technology that creates the problem can also help solve it. AI is accelerating materials science for clean energy. Researchers are using AI to discover new materials for solar panels with higher efficiency, new electrolytes for batteries with greater capacity, and new catalysts for carbon capture. These discoveries could take decades through traditional trial and error. AI is finding candidates in weeks. Climate modeling has been revolutionized by AI. Models that used to take months to run on supercomputers can now be approximated by AI in hours. The result is more accurate predictions, better understanding of climate dynamics, and more effective policy responses. AI is also being used to optimize electrical grids, balancing renewable energy supply with demand in real time. The intermittent nature of solar and wind requires sophisticated management of when energy is stored, when it is used, and when it is sold. AI can do this optimization at a scale and speed that humans cannot. So the question is not whether AI can be used for environmental good. It absolutely can. The question is whether the environmental benefits of AI outweigh the environmental costs. And right now, the honest answer is that we do not know. The costs are large and growing. The benefits are potentially large, but largely unrealized. There is also a fundamental distribution question. The benefits of AI accrue primarily to technology companies, their shareholders, and their users, who tend to be wealthier people in developed countries. The environmental costs are borne disproportionately by communities near data centers, often rural and lower-income communities. If you live in Goodyear, Arizona, you did not choose to host a Microsoft data center that consumes 56 million gallons of water per year. You did not get a vote. The economic benefits flow to Microsoft and its shareholders. The water scarcity affects you and your community. This is an environmental justice issue. Regulation is beginning to respond, but far too slowly. The European Union Energy Efficiency Directive now includes data center reporting requirements. Operators must publicly disclose energy consumption, water usage, and renewable energy utilization. Transparency is the first step toward accountability. Singapore imposed a 3-year moratorium on new data centers construction in 2019, later replaced with a selective approval process that requires meeting strict energy efficiency and sustainability criteria. The city-state recognized that it could not power unlimited data center growth on a small island with limited energy resources. The Netherlands, Ireland, and parts of Germany have implemented various restrictions on data center construction, primarily driven by grid capacity concerns rather than environmental concerns. The grid physics of AI demand are colliding with the grid physics of national electricity infrastructure, but regulation is moving at government speed. AI infrastructure is being built at Silicon Valley speed. The gap between what is being deployed and what is being regulated grows wider every month. By the time meaningful regulations are in place, most of the planned data center infrastructure will already be constructed and operational. Here is the uncomfortable reality that nobody in the AI industry wants to state explicitly. The current trajectory is physically unsustainable. Semiconductor efficiency improvements, which historically doubled every 2 years under Moore's law, are slowing down. Meanwhile, AI model size is growing faster than ever. If AI adoption and model scaling continue at current rates, while chip efficiency improves at projected rates, the energy requirements for AI will exceed what most national grids can supply within the next decade. This is not a prediction. It is arithmetic. The industry has 3 possible paths forward and will likely pursue all 3 simultaneously. Path 1. Make AI dramatically more energy efficient. Path 2. Build massive amounts of new energy generation, including nuclear. Path 3. Accept that unlimited, nearly free AI access was always a temporary fantasy. On Path 1, there is actually good news. The AI industry is making real progress on efficiency. Smaller, more specialized models are matching the performance of much larger general models. Techniques like model distillation, quantization, and sparse activation routes are dramatically reducing inference costs. Mistral, the French AI company, has demonstrated that smaller models trained on higher quality data can match or exceed much larger models. Their approach suggests that the brute force scaling approach may not be the only path to capability improvements. Apple on-device AI models are another example. By designing models specifically for their hardware, optimizing for their neural engine chips, they achieve capabilities on a phone that previously required a data center. On-device inference is inherently more efficient because it eliminates transmission overhead. On Path 2, the nuclear renaissance is real and accelerating. Beyond the Microsoft, Amazon, and Google deals, dozens of nuclear startups have raised billions in venture capital. The AI industry energy demands are creating the economic case for nuclear power that climate arguments alone never achieve. Small modular reactors, if they achieve regulatory approval and economic viability, could be deployed alongside data centers, providing dedicated carbon-free baseload power without long-distance transmission losses. The AI industry could become the anchor customer that makes SMRs commercially viable. Path 3 is the one that AI companies do not want to talk about. The era of free, unlimited AI access is probably unsustainable. When compute costs real money, when energy has real environmental impact, the economics of giving away AI inference will start to break down. OpenAI already has a tiered pricing model. Free users get a limited model. Paying users get better models. Enterprise customers pay even more. This tiering is partly a business strategy, but it also reflects the real underlying cost difference between serving a simple model and a complex one. As AI becomes more deeply embedded in the economy, we will likely see more explicit pricing of AI based on compute consumption. You might pay a penny for a simple question and $1 for a complex research task. This could actually be a good thing because it would align the price with the cost and reduce wasteful usage. The environmental cost of AI should not be hidden. Every query should come with a carbon and water impact estimate, similar to the nutrition labels on food. Users should know that generating a 500-word article used as much energy as charging a smartphone, or that generating a high-resolution image evaporated a cup of water. This kind of transparency would change behavior. It would make people think twice before using AI for trivial purposes. It would create market pressure for more efficient models, and it would force AI companies to compete on efficiency, not just capability. Because here is the question I keep returning to. We are burning gigawatts of electricity and millions of gallons of water so that AI can write marketing emails, generate funny pictures of cats, and help students cheat on their homework. Is that really the best use of our planet resources? AI has the genuine potential to solve some of humanity's greatest challenges, to accelerate scientific discovery, to personalize education, to optimize global supply chains, to discover new medicines. These are worthy uses of energy and water. But if the majority of AI inference is going to low-value, trivial, or even harmful applications, then we are paying an enormous environmental price for very little human benefit. The question is not whether AI can be valuable. It is whether we are using it for valuable things. The AI energy crisis is not a simple story of good versus evil or technology versus nature. It is a story of trade-offs, unintended consequences, and choices that we are making right now, mostly without realizing we are making them. Every ChatGPT query is a small vote for more AI infrastructure. Every AI-generated image is a small draw on the Colorado River. The cumulative effect of billions of small, individually insignificant decisions is reshaping our planet energy landscape. The solution is not to stop using AI. The solution is to use it more intentionally, to demand transparency about its costs, and to make sure that the enormous energy investment is going toward applications that genuinely improve human welfare. That is the real AI energy story. Not a simple moral panic, a complex, urgent challenge that deserves far more attention than it is getting. If you found this analysis valuable, hit that subscribe button and turn on notifications. We do deep dives like this every week, going beyond the headlines to what actually matters. Next week, we are investigating something completely different: the AI education revolution. Students are using AI in ways nobody in the school system predicted, and the results are reshaping what it means to learn. In the comments, I want to hear from you. Should AI companies be required to show the energy cost of every query, like a nutrition label, or is the environmental concern overblown? I read every response and feature the most thoughtful ones. Thanks for watching. Stay curious, and I will see you in the next one.